great pleasure 2 months back in November 2017 to deliver this presentation for about 1.5 hours with Dr. Ajay Singh and Dr. Pratibha Warware and other colleagues and a lot of students. So today I shall really restrict myself to a short period. Now, the topic that I'm going to cover today is saline water intrusion in global coastal aquifers. So I shall basically introduce, the way I planned my presentation today is I'll just introduce the topic, how seawater dives under the fresh water, how overpumping causes upwelling and exacerbates problem, coverage of some geographies. Today I limit myself to parts of South Asia and West Asia, then some theoretical studies, then a case study of a district, a coastal town, and a possible solution measure. So these are in brief the segments of my rather brief presentation that I'm planning to deliver right now. So, okay, so the next slide please. Next slide. Okay, so this is just an introduction. Next slide. Next slide. So these are the factors affecting coastal salinity. Okay, next slide please. Okay, so this is the status in India. So we have the east coast and Gujarat highly affected. Rest of the west coast, Maharashtra, Karnataka, Kerala, because of the western Ghats, not so much affected. Next slide please. Next slide. Okay, so this is some key points for South Asia that we know. So we adopt 2D mathematical modeling, not 3D modeling, because that's rather too cumbersome at this particular point of time. Next slide please. Okay, so India is divided into 16 regions based on hydrogeology. This is just one classification. There may be more classifications. Next slide. So this is the Ganga Basin restricting to India. Okay, this is West Bengal, the coastal area. Next slide. Okay, this is the undivided Midnapur district of West Bengal, a coastal district which is now subdivided into smaller districts subject to saline water intrusion. Next slide. Okay, so this is previous slide. So this is from the Geological Survey of India, the part of Midnapur district of West Bengal and the northernmost part of Orissa state that are subject to saline water intrusion. Next slide. Next slide. Okay, so this is the Hooghly district, which is not a coastal district, it's an inland district, but it is nevertheless subject to saline water intrusion because saline water intrusion is very serious. Next slide. So this is Bangladesh, and Bangladesh is also subject to saline water intrusion. Next slide. Okay, so this shows that this southern part of Bangladesh is subject to saline water intrusion. The Chittagong, Cox's Bazar area is not so much subject to saline water intrusion because of the Chittagong hill tracts. Okay, so next slide. Okay, so this is some general conclusions regarding India and Bangladesh, one can say, and high heterogeneity in coastal aquifers, etc. So these are more or less. Next slide. Okay, so in West Asia we covered parts of West Asia, UAE and Qatar. Next slide. Okay, so this is this map was taken from the Saudi Geological Survey. So what this gives a very good idea of the entire Arabian Peninsula. So we found that on the Persian Gulf Coast there is Aeolian sand, except for a little bit of hills on the UAE-Oman border. So there is intense saline water intrusion in this part of Saudi Arabia, Bahrain, then UAE, Qatar, Oman. On the Red Sea coast of Saudi Arabia, there is not so much of saline water intrusion, because that's entirely because of the geographical configuration. Yemen in the south, again not so much of saline water intrusion on either the Arabian Sea coast or on the Red Sea coast. So by far the greatest amount of saline water intrusion occurs in this Persian Gulf coast. Next slide. Okay, so this is again showing the same thing in greater detail. So this shows that in this these parts, UAE, Qatar, Bahrain, then Dhahran in the Gulf coast of Saudi Arabia, these are subject to intense saline water intrusion. And drinking water, this is again from the Saudi Geological Survey, and drinking water is primarily obtained by desalination, which consumes energy and is energy intensive. It consumes a lot of energy. Okay, next slide please. Okay, this is Israel. Now Israel has a national water carrier which conveys water from the northern part to the Negev desert in the south. So this is the Dead Sea. So Jordan is now building a Red Sea link, because the Dead Sea is in a very bad condition, and this is the Jordan River. So actually I visited the site where Jesus was baptized by St. John the Baptist, and the Jordan River coming out of the northern side of the Dead Sea, that is also in a very bad shape, highly polluted and highly contaminated. So Jordan is building their national water carrier from this Aqaba port region to the Dead Sea, to rejuvenate the Dead Sea with the water from the Red Sea. Yes, next slide. Okay, so this is just a topographic map of Israel showing that elevation of Jerusalem is high. This is the Mediterranean, this is the Dead Sea. Well, parts of the banks of the Dead Sea that I visited were actually lower than the... Yes, next slide. Okay, so this is another geological map of Israel showing the same thing. Okay, next slide. Okay, next slide. This is something about UAE and Qatar. Next slide. Okay, so this is UAE, highly affected by small country, but highly affected by saline water intrusion. No rivers over there. So drinking water is a big problem. Desalination. Next slide. Qatar again, similar problem, similar solution, desalination. Again, energy expensive. Next slide. Okay, so this is some sort of a mathematical model. We know that seawater being denser than fresh water dives under the fresh water. We have assumed a sharp interface called the Geiben-Herzberg given by the Hagen-Hertzberg equation. That's not strictly speaking very accurate because there's a density gradient which is too difficult to be considered in the modeling. Next slide please. Okay, so equating, we have found the depth, equating the pressures, we have found out the depth of this interface, again considering sharp interface. Next slide. Okay, so this is a deep tubule. What happens beneath the deep tubule is that there is I'm taking an unconfined aquifer, so there is a drawdown near the deep tubule, so naturally the freshwater pressure decreases in the vicinity of the deep tubule, and naturally since the counterbalancing freshwater pressure decreases, the seawater rises beneath the deep tubule, and since the drawdown is the greatest at the tubule, the top of the cone, we call it upconing, is just below the center of the well. Next slide please. Okay, so this is equating, there's an equation given called the Dagenberg equation for the upconing, and equating that with the drawdown and taking time up to infinity, considering a steady state condition, we got the permissible discharge from this deep tubule to be given by this equation. Now the entire point is that if you can eliminate this deep tubule and make a shallow structure, then we benefit on two counts. First of all, the base of the structure is located at a much higher elevation, and the upconing is much less. So here, if the discharge exceeds this permissible discharge, what will happen is this is the critical discharge at which the top of the upconing is just at the base of the well. So any discharge greater than this, the deep tubule will start pumping out saline water, which we don't want. So we want to, our proposed solution is a shallow structure which will have a higher bottom elevation, and the top of the upconing will also be lower, so this problem will be eliminated. But how do we get a good discharge with such a shallow structure? We'll come to that a little later. Okay, next slide. Okay, so this is again, we have considered homogeneous aquifers and all these routine observations. In the Arabian desert, the sand is Aeolian sand. So for the Aeolian sand, the horizontal transmissibility is much greater than the vertical transmissibility. So there is intense horizontal transmission of water inland. Okay, next slide please. Okay, so we have proposed a horizontal infiltration gallery. Next slide. Okay, in Arabia there are historically almost horizontal infiltration galleries called qanats. Now we have not found out in Persian they are called qadis. So we have not found out an English equivalent, so we have used the Arabic word qanat throughout our work. Okay. Next, now the most famous qanat is a very famous picture of a qanat emptying into the National Library of Iran in Tehran. Okay, so these are what we did. Okay, next slide please. Next slide. Okay, so these are just some literature survey. Next slide. Okay, so again literature survey. Okay, next slide. Next slide. Okay, next slide. Okay, now this diffusion zone or mixing zone we have not considered, very obviously. Okay, we have considered sharp interface. Now, next slide. Again, this is another drawing of basically what I've said already. Next slide. So this is one literature survey, but I've summarized this. Next slide. Okay, so this is considering the geochemical signature. So next slide. Okay, so this is another equation. Okay, next slide. Okay, so this is the salt wedge at the sea coast, and okay, next slide. This is in a multi-layered aquifer. This is extremely complex to analyze, so we are yet to do that, I should say. We have only considered a homogeneous thing. Next slide. Okay, again multi-layered aquifer. Okay, this is somewhere in the United States. Next slide. Okay, mixing zone. This is a transition zone. This is saline water. This is fresh water. The salinity decreases in this mixing zone, but we have not modeled that. We are yet to do that. Okay, next slide. Okay, again Heisenberg formula for sharp interface. Next slide. Okay, again shows very clearly. This is deep tubal. This is upconing, and this is the gap. So deep tubals in coastal areas aggravate the problem. Next slide. Okay, again this is concentration contours. So the upconing does not occur just as a sharp interface, just as the saline water intrusion does not occur as a sharp interface, simply because there are concentration variations. But again, this concentration variation we have not considered in our model. We are yet to do that. Next slide. Okay, these are some studies that we did and some results that we got from our formula, using our formulas. Next slide. Okay. Now these are just some theoretical works that we did. Next slide. Okay, so this is what is called Purbo Midnapur district now. So it's just part of the original Midnapur district. But this is the part of the Midnapur district which is adjacent to the sea. Nothing special about this district. This district was simply chosen as a case district for study. That's it. And many points on this district, many locations were taken in this district, in Purbo Midnapur. Next slide, please. Okay, so this soil profile we got from Geological Survey of India. Next slide, please. Next slide. Next slide. Okay, so these are again some theoretical studies. Pre-monsoon depth to water level in 2004 in Purbo Midnapur, West Bengal. Next slide, please. Post-monsoon depth, obviously higher because the water level goes higher after the monsoon. Next slide. This is a pre-monsoon piezometric surface contour. Next slide, please. Then a 3D pictorial view of the piezometric surface pre-monsoon contour, 2006. Next slide, please. Then salinity distribution and processes in Purbo Midnapur, but we were not able to model all this heterogeneity because it's far too complex to be modeled mathematically. Yes. Next slide, please. Okay. So study area and sample well location. So since it's extremely costly to dig our own wells to take out water. We were totally dependent on the deep tube wells that were dug by the government, and we took water from the deep tube wells that were dug by the government. Now, the difficulty with that obviously was that the distribution of the wells was not as precise as we would have wished it to be, and in some places wells were placed closely apart, in some places wells were placed a little far apart. But we had entirely rely on what the government had done, and on at which spots they had dug the wells, we had no option but take water from those wells. Next slide, please. Okay, so chemical analysis of water samples. So we thought that since we are analyzing water samples, why not we analyze all the parameters, not only salinity. Although the ambit of our work did not really extend to other parameters like chloride, rather except chloride.
This complete.
Yes. Next slide, please. Yes. So chloride concentration, then probable path of saline water ingress. Okay. Next slide. Okay. So total dissolved solids. Okay. Next slide. Okay. So some abundant wells. You can see pictures. Next slide. Okay. Next slide. So these are just some laboratory tests. Next slide. Next slide. So when sand is dissolved in saline water at different temperatures of saline water of different concentrations for different periods of time, the hydraulic conductivity changes. So we did a lot of experiments on that. So in open channel with porous media. Next slide. We did some experiments. Next slide. Next slide. Next slide. Okay, next slide. Next slide. So this is we plan horizontal wells with shallow horizontal wells with vertical riser. This is what we actually proposed. These have to be designed. Next slide. So we developed some formulas for that, and four-legged canna. You can have any number of legs as you like, 3, 6, 2, anything. Next slide. So again, some equations for this. Next slide. Next slide. Next slide. Okay, we took a particular geographical location, a particular study area. Next slide. And some laboratory tests. Next slide. Next slide. So next slide. Next slide. Okay, so regarding conclusions, so I basically our basic solution was a shallow crossed horizontal well come riser system, giving sufficient discharge. All the diameters, depth, lengths of the arms, etc., everything has to be designed. Next slide. Next slide. Next slide. Next slide. Okay, so these are some. Next slide. Okay.